What is critical load in structural buckling? Imagine a tall, slender column standing under pressure. It looks sturdy, but at some point, it might suddenly bend or collapse. That moment is linked to something called the critical load. The critical load is the maximum amount of compressive force a structure like a column or beam can handle before it suddenly buckles. Buckling is a failure mode where the structure deforms sideways, not because the material has broken, but because it becomes unstable. This shape change can happen even if the material itself is still strong enough to resist breaking. When the load reaches this critical point, the structure shifts from being stable to unstable. Below this load, it stays straight and can carry weight safely. But once the critical load is hit, tiny sideways movements grow rapidly. This can lead to the structure bending, bowing, or even collapsing. It's like pushing a pencil until it snaps sideways. It doesn't break first, it just suddenly buckles. The critical load depends on several factors. The material's stiffness, measured by Young's modulus, plays a big role. A stiffer material can carry more load before buckling. The shape and size of the structure matter too. A thicker or wider cross-section makes it more resistant to buckling. The length of the structure is also key. Longer columns tend to buckle more easily, so their critical load is lower. How the ends are supported influences the effective length. For example, if the ends are fixed or pinned, it changes how much load the structure can handle before buckling. Engineers often use a formula called Euler's formula to calculate the critical load for slender columns. It involves the material's Young's modulus, the moment of inertia of the cross-section, the length of the column, and an effective length factor based on end conditions. The formula shows that the critical load decreases as the length increases and increases with stiffness and cross-sectional strength. For example, shortening a column or making it thicker raises its critical load, making buckling less likely. Understanding the critical load is essential because it highlights a failure mode that isn't about the material breaking but about the structure losing stability. Sometimes, slender components can fail suddenly under moderate forces because they reach this buckling point. Recognizing and calculating the critical load helps engineers design safer structures. They can reinforce members, choose stronger materials, or adjust lengths to prevent buckling. In real-world applications, avoiding buckling involves increasing the cross-sectional stiffness, using stiffer materials, adding supports or braces, and designing end conditions carefully. Ignoring this concept can lead to unexpected failures in columns, beams, or frames that are under compression. That's why understanding the critical load is a key part of mechanical failure analysis and structural safety.